Hey everybody, Mr. J here. Welcome back to Chem Talks. Today, guys, we are going to take something that you've probably been doing for years and apply it to chemistry. And that's figuring out percents, right? One of probably the most common places you figure out percent is when you want to know how you did in a test, right? Let's say a test was worth 100 points and you scored 95. How do you do that? Well, you just go 95%, right? Well, that's true, but what did you do? You took your 95 points that you earned, divide that by the total points the test was worth, 100 times by 100, gave you 95%. Well, let's say a little harder. Let's say the test was worth 50 points and you scored 40 on. How would you figure out your grade? Same thing. You're going to take 40 divided by 50 times it by 100, and you get, that's right, 80%. Well, we're going to do the same thing today and apply it to chemistry. That's what we call percent composition in chemistry. So it's no new math, it's what you've already done. So let's see how this applies to chemistry. All right, here we go. So when we talk about percent composition, we can define it as the percentage of each element present in a compound. So if we're looking at sodium chloride, what percent of that compound is sodium? What percent of that compound is chlorine? Okay. When we say percent, we're talking about percent by mass. Okay. 50% of it is sodium, 50% is chlorine. Now that's not what it is, but that's kind of thing that we are talking about in this podcast today. So let's look at an example here. Let's say we have magnesium phosphate. Now, before we even start, let's remember magnesium has a +2 charge, phosphate has a -3. So we crisscross our charges, right? Don't forget the parentheses around the phosphate. Don't forget what you've already learned, guys. This is really important. So if we're given magnesium phosphate, we could ask a question something like this. What percent of the mass is due to magnesium? And in order to be able to do that, we need to pull in something that we've already talked about this unit, and that's the molar mass, right? How much does 1 mole of this compound weigh? We could also do it percent by mass in AMUs if we're talking about one molecule, but we've talked about how the mole is probably a more practical unit to use. So let's talk about how we can calculate this percent composition. It's pretty simple. Okay, the first thing we need to do is find the molar mass of it, and we've already learned how to do this unit. Okay, once we know the total molar mass, we can find the mass of the element that we are given in. If you write this correctly, it's super easy to do, and divide the mass of the element we're interested in by the total molar mass. Okay, it's kind of like what you got on a test divided by what the test's worth, and then we're going to multiply it by 100 to get the percentage. So real simple. We're taking what you've learned already, what you've done already for years, figuring out your grading test, and just applying it to chemistry. So if we look at an equation, here it is. The grams of the element that you're interested in, total grams, okay, divided by the grams of compound or the molar mass of compounds, and we're going to multiply that by 100. Okay? This you will need to have memorized, hence the big, bold memorize here. Okay, you'll need to know this for the test. Okay, but you already know this equation. It's nothing new. We're just applying it new. Let's go ahead and take a look at that magnesium phosphate. So our question was what percent of the mass is due to magnesium? Well, luckily we already were given the formula, so we already know that. But now first thing we have to do is figure out the molar mass. So when we do this, we look at our subscripts. Well, we know that we have 3 magnesiums. Okay, and if we look up magnesium on our periodic table, it has a molar mass of 24.31 grams. Now phosphate, we have a 2 out here, so remember we multiply the exterior subscript by the interior, so 2 times 1, so we have 2 phosphates, okay, at 30.97, and then we have oxygen, we have 4 here, multiplied by 2, so we have a total of 8 oxygens at 15.99. I rounded that wrong, it should be 16.00, but close enough for us, okay? So here's the 4 on the inside, here's on the outside. I would just multiply it by 8. And then to find the molar mass, we write it all down. Now, when you are doing these problems, I really, really suggest that you write this all out like this. Why? Because the next step is much easier. So we want to know what the percent mass is due to magnesium. So what's your grade on this? Well, here's the total mass of magnesium. That's kind of like your grade. Here's the total molar mass of it. It's kind of what the test is like, okay, or what it's worth. So if we take your score divided by the total, multiplied by 100, we can get percent of magnesium. So let's look at that. So we're going to take 72.93 grams Divide that by the total molar mass at 262.79, times it by 100, and you get 27.75% magnesium. So 27% of whatever, roughly 27% of whatever amount we have is going to be due to magnesium. The rest is due to the phosphate and the oxygen in there. So pretty simple. Let's try one more. Let's try another one. So we have this formula here, C2H22O11, okay, covalent compound, and it wants to know what's the percent composition carbon. Once again, this is an easier one because it gives us the formula right away. So we know we have 2 carbons at 12.01 for a total mass of carbon of 24.02. Hydrogen, we have 22 at 1.02, and then oxygens, we have 11 at 16.00. There it is, rounded correctly. Okay, and we add all these up. Now, when we have in this order, it makes it really simple, right? Because it wants to know carbon. Well, we know carbon is 24.02. We're going to divide that by the total and multiply it by 100. Okay, so take our 24.02. That's the element that we're interested in, the total mass, not just the molar mass, but the total mass of that. Divide it by the molar mass of the compound and times by 100. So in this compound, 10.81% of its mass is due to carbon. So pretty simple. Okay, what I'd like you to do, here are 2 problems. What I'm going to have you do in just a moment, I want you to pause the video and try to figure out the percent composition that the question's asking for each of these, okay? So go ahead now and pause the video. Don't cheat, pause it, and work these 2 out. And then once you've done, go ahead and hit play, and we will see how well you did. All right, pause me now. No, I'm talking to you. You didn't pause me. Go ahead, hit the pause button, and do this. Trust me, you'll thank me later when you can do this on the test. So pause it, come back and see me. All right, we'll pretend you guys actually paused this. Hopefully you did. Remember, if you're not doing the work, you're not going to get out the results. So do the practice problems. So the first one said, what in calcium hydroxide, what's the composition, percent composition of oxygen by mass? So first thing we have to do is remember the formula. Calcium has a +2 charge. Hydroxide, this is hydroxide. Remember, oxys are big, which means this is the OH minus, not the H. So +2 minus 1 on here. So our chemical formula is CaOH2. Don't forget the parentheses. Remember, hydroxide, we said it's really easy to forget, so don't forget those parentheses. Now let's figure out the molar mass. Well, I have 1 mole of calcium, and then oxygen, the 2 goes to that. So I have 2 moles of oxygen and then 2 moles of hydrogen for a total, when I add this up. Now I got a little typo here, sorry if I change that. It's not 410, it's 40.08 to get next to the 0. But my answer is correct anyways. It's 74.10 grams. So now what I'm going to do, I'm going to take my molar mass of oxygen of 32, divide it by 74.1 times by 10, and I got a percent of oxygen of 43.18. Did you get that? Hopefully you did. If not, pause real quick and see where you made your mistake. Now, if you round it correctly, like we've talked about in class, you should get the right answer. Okay, remember when we take something off the periodic table, the molar mass of it, we're going to take the 2 decimal places and round immediately. All right, let's look at that second one. The second one said we have ammonium nitrate. Ooh, we got a poly and a poly put together, and it wants to know what the percent of hydrogen is. So ammonium, NH3, and nitrate, NO3, both -1. I'm sorry, ammonium's NH4. Thinking ammonia. Okay, so plus minus there. Now, something to be aware of. When we go to figure out our molar mass, we got nitrogen here, and we also have nitrogen there. So pay attention to that. So our 3 compounds, we have nitrogen, hydrogen, oxygen, but we have 2 nitrogens. Even though it's in 2 places, it still counts towards the weight. We have 4 hydrogens at 1.1, and then we have 2 oxygens. So we add those together for a total molar mass of 64.06. Now, it wants to know hydrogen, so look, I have that data right here. This is why I write this out, so I can find it really quick. So I'm going to take 4.04 divided by 64.06, multiply 100, and I get 6.31% hydrogen. So pretty simple. It's like I said, it's the calculation you've been doing for years when you're figuring out your gradient test. Now we're just applying it to a new situation or something new. So hopefully this is not too hard. Probably the hardest part of this is making sure you get the right formula, which is always a challenge for us. All right. Let's look at a slightly different problem. In this problem, it says find the percent composition of a compound that contains 17.6 grams of iron and 10.3 grams of sulfur. So the first thing you notice, they don't give us a chemical formula for us. And this one's important because remember, iron's one of those variable charges. It can be a +2 or +3. We don't know for sure. But what we do know is we have these two parts that make up the whole. So if we add our amount of our grams of iron and our grams of sulfur together, we get the total mass, which comes up to 27.9. So if we want to know the percent of each of these, that's easy. We take 17.6 grams of iron divided by the total mass times it by 100, and we get 63.08 grams. Okay, now there's two ways we can figure out sulfur. Okay, first one is we take 10.03 grams divided by 27.9 times 100, and we get 36.92. The other thing we could have done, since there's only two compounds, once we know there's 63.8 grams of iron, we know the rest of it's got to be the other. What a percent's always add up to 100. I could take 100 minus 63.08 and got 36.92%. Either way is acceptable for me. Just make sure if you're doing subtraction method, you show your work as well, okay? Because all your work is worth points. Remember that. Okay, so we are able to find out the percent composition of the elements in here without knowing the formula. Okay, so I made it pretty simple that way. Okay. So, there's the same problem there. We'll ignore that. Okay, here's the thing about percent composition. Unless we change the chemical formula, change the subscript somehow, the percent is going to be the same. And remember, if we change the subscripts, we've gone and created a new product, right? H2O is very different from H2O2. We got water and then we got hydrogen peroxide. So as long as we don't change the subscript, we can find out that the percent composition is going to be the same for a compound, whether we have 1 gram of it, 10 grams, 1,000, a million grams, a trillion grams, whatever. Okay, it's the same. And we can use that to figure out how much of a certain element that we might have in any given amount. Okay, and it's going to kind of come back a little bit to sound very similar to what we talked about when we figured out the average atomic weight when we were looking at isotopes of percent abundance. We're going to do the same thing, except rather than percent abundance, we're going to have the percent composition in the same way. Okay, so let's look at potassium phosphate. Potassium phosphate, first thing we got to do is figure out the formula. Potassium is what element? Hopefully you just said K, not P at this time of year. And then phosphate is PO4 in a poly, and it's a -3, so +1 -3. When we crisscross, we get K3PO4. Okay. So the first thing that we're going to want to know is what's the molar mass of this. I'm going to go ahead. Why don't you pause this and figure that out really quick? I'm not going to do all the work here, but figure it out, and then we'll come back. All right, did you figure it out? Hopefully you wrote it out because you're going to need it later. But our molar mass of potassium for 1 mole is 212.27 grams per mole. Okay. And so if they want to know what the potassium, maybe they're going to ask, what is the percent composition of potassium? Well, that's pretty easy. Now, hopefully you did the math earlier. What you found out when you did it is the total mass of potassium came out to 117.3 grams. We're going to divide that by the molar mass times 100, and we get 55.26% potassium. Now, that's going to hold true whether we have 1 gram, 2 grams, 100, 1,000, and so on. Okay? Let's say this was your test, right? If you got 55.26% points on a test worth 100, that's not doing too good. Okay? If you got 55.26 points on a test worth 50, that's doing really good. Okay? So let's see how we can use the idea of constant composition to figure out how much potassium. Let's say we had this problem. If you're given 1,208 grams of potassium phosphate, how many grams of potassium would you have? Well, the first thing you would have to do is figure out what's the percent of potassium in that. And we just did that. We found that in potassium phosphate, it was 55.26% potassium. Okay. So what we know that of 1,208 grams, 55.26% is going to be potassium. So we do this kind of like when we talked about our fractional abundance with isotopes. We're going to take our total mass, which is 1,208, multiplied by the decimal form of our fraction, of our percent. So 55.26% becomes 0.5526. And we multiply them together, okay? All we did, remember, to get this number, we can move our decimal place 2 points, or if you don't like moving it, you can divide it by 100. Okay, either way. But in 1,208 grams of potassium phosphate, we should have 667.54 grams of potassium. Pretty simple. The other way you could write this, if you don't like moving decimal places, Okay, you can just take the mass times the percent and then divide it by 100. This is what we did right here. By moving decimal, we didn't have to divide it by 100. Get the same answer. I don't care which way you do it. Um, I always like just moving it because that's easy for me, and entering things in the calculator is hard. So for me, it's easier to do it this way. It's one less calculator. Either way that you want to do it is fine with me. All right, see if you can do this one on your own. How many grams of sulfur are found in 600 grams of sodium sulfate? So first thing you're going to have to do, figure out your chemical formula, find its molar mass, find the percent composition of sulfur, and then apply that to 600 grams. So go ahead and pause it. Please pause it. Do the work. Remember, hard work pays off in the end, meaning it'll improve your test grade if you do the work. And then come back once you're done. I'll sit and twiddle my thumbs for a second, pretending that you're actually doing this. You better be doing this. Okay. All right, hopefully you did that problem on your own. Here we go. So we know sodium is a +1, sulfate SO4 -2. So when we crisscross, we get Na2SO4 for our chemical formula. Now we have to calculate how many it is. Well, we have 2 sodiums. Oops, that should be a 2, not a 1. 2 times 22.99 gives us 45.98. We got 1 sulfur, and then we have 4 oxygens to give us hopefully a total of 142.05. Okay, so to figure out how much sulfur is in this, really easy. We're going to take our 32.07, divide it by 142.05. Okay, and so we know that in sodium sulfate, it's 22.57% sodium. Or excuse me, sulfur, not sodium. All those S's get me confused. Now what we want to do is we want to apply this to 600. Ask, well, in 600 grams of sodium sulfate, how many grams of sulfur do we have? Well, we're going to change our 22.57 to a decimal, multiply it by 600. So 600 divided by 22.57 is 135.42 grams. Now remember, you also could have just taken 600 times 22.57 and divided by 100. Either way is fine with me, whichever way makes it a little bit easier for you. All right, hopefully that went well for you. All right, we're going to talk about a second type of compound today, or it's a new type, and this is called hydrated. Now, when you talk about, hear the word hydrate, what do you think of? Well, for me, that means I'm drinking lots of water. I'm well hydrated. Okay, I've been drinking my 32 ounces of water a day, whatever it is you're supposed to drink. And in chemistry, that's what a hydrated compound means. It has water. So when ionic compounds form, okay, they form what we call a crystal lattice or crystal structure. Think of an aqueous solution. We talked about that, where the atoms are just, or the ions are floating around. As that dehydrates, as the water evaporates, those crystals come back and reform. Well, when they reform, what happens sometimes is that water molecules get stuck inside that crystal matrix and get trapped in there, and they can't escape. When this happens, we call it a hydrated compound. It's an ionic compound that has water trapped inside of it. Okay. When we calculate the formula way, the molar mass for these compounds, we must include the water in it, because we're not just measuring the ionic compound, we're also measuring the water that's inside of it. So for example, if we have this one, sodium carbonate, refer to that, okay, when it reforms, sometimes it's going to trap water in it, and we call this a hydrated crystal. Now, something really important to note is this dot here. When we see this in math, we think it means multiplication. In chemistry, it doesn't mean multiplication. What it means in chemistry is that it includes. It means includes. So if I have 1 mole of sodium carbonate, I'm going to have 10 moles of water included or trapped inside of it. That's what a hydrated compound is. Okay. So if we look at this hydrated compound, okay, the name of this would be sodium carbonate decahydrate. Okay, we use the same prefixes on the water that we use for covalent compound, and we use the word hydrate to do water. So let's say if we had Na2CO3 5H2O, it would be sodium carbonate pentahydrate. Okay, so we follow the same naming as we do with our covalent compounds. Okay, and remember, this dot doesn't mean multiply. We're not multiplying. It means it includes it inside of it. And so when we do the molar mass, we're going to have to include the water. So let's figure out how we would do the molar mass. So what I'm going to do is figure out the molar mass of sodium first, and that's pretty easy. We got 2 sodiums, we got 1 carbon, and we got 3 oxygen. Now we do have oxygen over here, but I'm going to keep those separate right now. So this would give us the molar mass of the sodium carbonate. Now for the water part, we have 10 times 2, so 20 hydrogen molecules, and then 10 times 1, we have 10 oxygen molecules. Okay, we add that all together and come up with a molar mass of 286.19. Now, unless the question is asking for the percent composition of water, I would do it slightly different. If it's asking for the percent composition, excuse me, of oxygen, I would probably do it this way. If it's asking for anything else, what I would do with my water is keep water as a whole. Kind of like when we balance the equation, we kept polyatomics whole. We're going to do this. Remember now, water is H2O. So it's got 1 oxygen, which is 16, plus 2 hydrogens, which would be 2.02. Water has a total molar mass of 18.02. If you can memorize this, remember it, or figure it out quickly, I would use 18.02 rather than breaking it down. So if I were writing this down, I would, when I got to here, I'd write H2O and I do 10 times 18.02. It just makes it a little bit easier. And we use this number so much that I'm okay if you don't show me where that came from for water. All right. So we could ask a question about this compound is what's the percent composition of water? Well, we found out that it had 45.98 grams of water and a total molar mass of 286.19. Okay, times by 100 gives us 16.07% water, just like we've been doing. The only difference is that we have to include the water in a molar mass. Real quick, see if you can do the percent composition of water on your own. Pause this and then do the calculation, come back. Okay, let's see, we had a total of 10 waters. Water's 18.02, so it's 180.2 grams water in 286.19 grams of the total compound. Okay, times by 100, so it's 62, almost 63% water in this compound. That's pretty big. Okay, so same thing we've been doing. We just have to remember that we're including water, and that dot means includes. Think of it as a plus sign rather than a multiplication sign. Okay, now what we can also do is we can get rid of that water. Think about washing your clothes, right? After you put them in the washer, you put them in the dryer. Why? We want to dry them. It spins them around. Some of that force in there shoots the water off. The other thing that happens is that it heats. What's heat do? Well, it causes that water to evaporate. We can do the same thing with hydrated compounds. We can evaporate the water out. And what we do is simple. We heat it. When we heat a compound, we drive the water off, and what results isn't what we call an anhydrous compound. So when I buy chemicals for our stockroom, I'll either buy hydrated compounds or I'll buy anhydrous compound, which already have the water driven off for us. Okay, and so if we know the mass of a hydrated compound before we weigh it, and then we heat it up and find out the mass afterwards, the difference between those two is how much water was in that sample. And we can use that information to find out what the hydrate is. Is that pentahydrate, hexahydrate, heptahydrate? Okay, so let's talk about how we can do that real quick. Okay, let's say we have barium chloride. Okay, the formula for barium chloride plus 2 minus 1, so it's BaCl2. Okay, the question you could ask would be something like this. What would be the formula of the hydrated compound if it had a formula weight, molar mass, of 244.27? This is the hydrated. So it's barium chloride dot some water. And that's what we're trying to figure out is how many waters go in front of them. Like we said, the formula for barium chloride is BaCl2. So first thing we want to do is find out the molar mass. So in 1 mole of that, okay, actually we don't even need to do that, sorry. All right, like we said, the formula for barium chloride is BaCl2. Okay, so what we know is that before we heated it had a molar mass of 244.27. If we figure out the molar mass of barium, we got 1 barium, 2 chloride. What we find out, it's 137.33, and then chlorine, we have 2 of those, we get a total molar mass of 208.23. This is what it should be if it doesn't have any water, but since it has water, it actually has a weight of 244.27. So we're going to subtract those two from each other and figure out what the mass of water is. So I'm going to take the weight with water, 244.27, divide it or subtract out our molar mass of just plain barium chloride, and the difference between those is 36.04. So when we heated this with our Bunsen burner, we got rid of 36.04 water. Now to figure out how many waters that is, what we're going to do is we're going to take the water we lost, divide it by the molar mass of water. If you remember, it's 18.02. So we take 36.04 divided by 18.02, and what we find is 2. So there were 2 moles of water in it. So this is our number before the H2O. So our formula for this compound is going to be BaCl2 dot, meaning includes, 2H2O. How would you name this? See if you can write the name really quick. All right, the name is real simple. The first part is the same way we're doing, barium chloride. And then remember our prefix in covalent for 2? It's di, so barium chloride dihydrate is the name of this compound. Okay, so we used the hydrated compound, we heated it, we drove the water off, found just the mass of barium chloride, and then figured out how much water we had driven off, and then divided it by the molar mass of water to figure out 2 waters. We'll do something like this in lab coming up. Okay. Now we can ask questions something like, calculate the composition of barium or chloride or water in barium chloride dihydrate. So to do barium, we take the mass of barium we had, because it's 1 barium, right? 137.33 divided by your total mass times 100, because it's 56. Now see if you can figure out the mass of chlorine and then the mass of water on your own. Go ahead and pause the video and do that, and then we'll come back. All right, chlorine, we had 2 of those, right? So it's 70.9 divided by 244.27 times 100 gives us 29.01. Now at this point, there's 2 ways we can find water. One, we know all the percentages add up to 100. So I can take 100 minus 56.22 minus 29.01, and that'll give us what's left, and what's left is the water. Or I can take my mass of water, which we figured out to be, by heating, 36.04, divide it by the total mass times 100, and we get 14.75. So hopefully all those numbers add up to 100 or really close. They might be just slightly off due to our rounding, but when I say slightly, within the hundredths. Okay, so that's how we can figure out the number for the hydrate if it's not given to us using the before and after. All right, one last thing that I want to talk about that we're going to need for our lab is what we call yield, or how much is produced. And there are 2 types of yields that we're going to talk about. The first is what we call theoretical yield. Okay? Theoretical yield is the answer that we get when we use the periodic table to calculate our answer. That's what we've been doing so far. We've been using the periodic table to figure out what we should get in theory. Now, when we go into the lab and do this experiment, we're going to get what's called the actual yield. The actual yield is the amount of product that is produced when the reaction is carried out in the lab. Now, if we did our lab really good, our actual yield and theoretical yield should be the same. But let's face it, nothing ever goes perfect in the lab, right? Your lab partner's not paying attention, spilled something, you bumped something, we're off slightly. Okay, so what we do is we can figure out how close our actual yield is to our theoretical yield in what we call percent yield. Percent yield is like your score on a test. How correct were you? And all percent yield is a ratio of your actual yield to your theoretical, to what you actually got on the test divided by what you should have got on the test. Okay, so what we're going to do is take our actual yield, this is a result of the experiment, divide it by the theoretical yield. Remember, we got this from our periodic table calculation, and then multiply it by 100. Our goal is that our percent yield is 90% or better. That means you're 90% right. Anything much more than that is getting a little bit sloppy. Well, what would reduce our percent yield? Well, in our experiment that we're probably going to do, we're going to heat a hydrated compound. We're going to try to drive off that water. One way to think of these hydrated compounds is like a popcorn kernel, right? Why does popcorn pop? Well, inside that kernel is water. As we microwave it, if you're microwaving it, we're heating that water, it turns to gas, and as that gas builds up, it creates pressure, which pops our kernel open. Well, our hydrated compounds can do the same thing. As that water goes off, it can start getting the non-hydrated parts, the ionic part, to start popping out. And if we don't heat it properly or we heat it too fast, what you'll do at the end of your experiment, you'll look down around your heating area, and there's going to be all these crystals. That's error. That's things that popped out that shouldn't have been, and it's not being included in your find the data. Okay, so this is the second thing that you're going to have have memorized on how to do. And we'll get more practices in the lab. All right, today, guys, we learned how to apply the idea of percentages to chemistry to figure out the percent composition. Same thing that you've been doing for years to figure out your lab. We then also learned what hydrated compounds are. Remember, those are compounds that contain water trapped inside of them from when they form. We talked about how we can get rid of that water by driving off that water by heating and evaporating. And then we talked about how the difference between what we call theoretical yield, what we should get, our answer should be using a periodic table, versus the actual yield we get from doing the experiment. And then we can take our actual yield, compare it to our theoretical to find out our percent yield, to find out how good of a job we did in our experiment. All right, guys, if there's any of this that doesn't make sense, please put a quick little question mark on your notes, and that way you can ask about it when we talk about it in class. All right, guys, hope this made sense to you. If not, we will go over it in class. All right, guys, until next time, take care.